This is the Electromagnetic Spectrum Concept 3 Notes of Waves for Pre-AP. We are going to be discussing the electromagnetic spectrum today. This is going to be written on your foldable that you should have already made. I have attached pictures of what the foldable looks like, and then each page actually has instructions of how you should cut it and fold it and glue it together. So you're actually going to be taking those notes on your foldable. All right, so let's go ahead and get started. So electromagnetic waves, they're electric and they're magnetic waves, and we've talked about electromagnetism when we talked about how we could put a nail inside a circuit and that nail would become a magnet, even though it's not a magnet without the circuit. So electromagnetic waves, keep in mind that they're very similar concept. We have these electrons flowing through this through these waves, and it makes it magnetic. So we're able to transfer energy through a vacuum. Now, a vacuum would be like space. You do not have to have a medium to travel through like some of our other waves that we've talked about. So these, remember how when we talked about how longitudinal waves, we stood close together and I pushed one of you and it transferred through, the energy transferred through the rest of you. That had to have a medium to travel through, but electromagnetic waves do not, so they can exist without any form of matter. Now, electromagnetic waves travel at the speed of light, which is 300 million meters per second in a vacuum. So as you increase matter, they slow down. So that means that they're going fastest in a vacuum, and then it would be next in a gas, and then liquid, and they would move slowest in a solid. All right, so let's talk about waves versus particles. So waves are a disturbance that can carry energy, and particles are pieces of tiny matter. So electromagnetic waves can behave as waves and particles. Those particles are called photons. All photons are just, it's a massless bundle of energy. So it's a bunch of energy wound up together and it can move. That's really all photons are. In the picture you can see someone is holding a cell phone, and now this is just a virtual image to help you understand a little bit better, but you can see how there's a bunch of different colors and they're all kind of clumped together, and it's moving in wave-like motion, but they're individual photons because they're bundles of energy. All right, so here is what the actual electromagnetic spectrum looks like. So a spectrum is a wave of, or a range of something. So when we talk about the electromagnetic spectrum, we need to talk about all the way from radio waves all the way to gamma rays. So there's a bunch of different types of waves that are considered electromagnetic. And when we all put them together and we organize it, it's considered to be the electromagnetic spectrum. Now, we can shorten this to EMS or just EM radiation. So you may hear it coined or termed as EMS or EM radiation. So the first thing that we're going to discuss is a little mnemonic that talks about it, and it's Roy G. Biv. So it starts with radio waves, that's the R, and then we have microwaves, infrared rays, visible light, and that's where we start with the Roy G. Biv. So radio, micro, infrared, that is not Roy G. Biv. Ultraviolet, X-ray, gamma, not Roy G. Biv. Visible light is the only one where we use Roy G. Biv. So let's talk about let's look at the very far left side at radio waves. So you can tell that the wavelengths are longer as we travel right across the spectrum. So radio waves have the longest wavelength, which means they have the lowest frequency and the lowest amount of energy. As we travel across the spectrum to the right, we can see that the wavelengths are slowly getting shorter all the way until we get to gamma rays, to where it's the shortest wavelength, it has a much higher frequency, and it carries much more energy. All right, so let's break these down into the different waves. So we have radio waves. Now, radio waves are, they emit radio stations. So we can get like the FM or the AM radio stations. We also use this for Wi-Fi and TV, radar, MRI, cell phones. It's the longest wavelength, has the lowest amount of frequency. These are normally considered very unharmful. Like, we are around radio waves all the time. Like, just by having the Chromebooks in the classroom, they are emitting radio waves. Or having your cell phone in your pocket, they're emitting radio waves. Or having Wi-Fi in the classroom, radio waves. So they are very unharmful. But you need to know that they're the longest wavelength with the lowest frequency. So the wavelengths are about 100 kilometers to 100 meters. So basically what that means is it could be as long as a skyscraper or as long as a human. So it's a very large spectrum of size, but just know that they are the longest wavelengths, and that they are very, very big. All right, let's go to the next one, which is microwaves. So microwaves are used for cooking. They're used for Doppler radar and GPS. They are a little bit shorter, so they're about 0.1 meters, which is about the size of a butterfly. But so the Doppler effect is what we're actually going to talk about later, and I have a couple activities that we're going to do with it, hopefully tomorrow or Wednesday maybe. It's just a cool little toy that we had to play with. It's like a ball. But microwaves are also not harmful. You use them all the time when you stand next to your microwave while you're heating up your Hot Pocket or your Pop-Tarts. You're being, it's experienced microwaves. And so they are shorter than radio waves, but we use them very often. The next one is infrared waves. So infrared waves are used for like night goggle vision, remote controls, infrared photography. So you can see a picture of all of those things at the bottom. They are 0.0001 meters, so they're very tiny. They're about the size of a needle point, which would be not the head of the needle, but the sharp pointy end of the needle. That's very tiny. So they're much smaller wavelengths than microwaves and radio waves. But they're also not very harmful either. So these actually detect like a heat. So you're able to see, like if you use those night vision goggles, then you're able to see those wet heat waves that we're going to be talking about soon, which is super cool. All right, now visible light. Remember, this is the one where I said Roy G. Biv. Remember that. So visible light waves, it's the only electromagnetic wave that we can actually see. So like if we go back and we talk about infrared waves, well, we can only see infrared waves because we have the night vision goggles. So we can see almost everyone can see every light wave in the visible light spectrum. So it's given off by the sun and by light bulbs. Now, inside the visible light, we also have different wavelengths. So like red is going to have the longest wavelength. Then it'll be orange, then yellow, then green, then blue, indigo, and violet. So as you look at the rainbow, you can see that the wavelength is determined by, or the color is determined by the wavelength. So different wavelengths are going to slow down when they hit different mediums. And we saw that when we looked at prisms and we talked about refraction. So like your red slowed down because it's going at a different speed than your indigo because they have different wavelengths. Now, these are super duper tiny. They are about the size of a protozoan. And remember, we talked about protozoans last year in life science. All right, so let's keep going. The next one we're going to talk about is ultraviolet waves. So these are dangerous to the human body. They're not terrible though. They actually keep us healthy. So like they help us produce vitamin D. They can kill bacteria. It's used by light bulbs. But if we are exposed to them too often, it can cause skin cancer. This is what the sun gives off. It can cause skin cancer. It can damage our vision. So, short amounts is very helpful for us. We benefit from it, but a lot of exposure to it could be bad. But this is the size of a molecule, so they're very tiny. But we need ultraviolet lights to be able to survive. On the next one, it is an X-ray. So X-rays can they're able to penetrate or go through soft tissue, and so we're able to take pictures of our bones because of that. So they're used in CAT scans and X-rays to be able to see fractures or bones, and they are small enough that they can penetrate these skin cells. But overexposure can cause cancer, just like with ultraviolet light. Now, these are very tiny. They're about the size of the atom. So they have to be smaller than a skin cell in order to be able to go through it. So they're the size of an atom. Gamma rays is the last ray, or the last waves on the electromagnetic spectrum. So they are the smallest wavelengths. Now, these are used to kill cancer cells. They're also used to sterilize medical equipment, and they're used in radioactive trackers. So when an individual has cancer, they can go through radiation. And when they go through radiation, they are literally taking in gamma rays, and these gamma rays are used to kill the cancer cells. They are the smallest wavelengths, and they have the highest frequency. And they're about as small as an atomic nuclei. So they're the smallest thing possible. And they are very dangerous. Now, we're done talking about the electromagnetic spectrum waves, but we need to talk about the Doppler effect. So the Doppler effect is super cool. Ambulances use it. Police officers use it. It's any of those sirens that you can hear from the back of you, but when they pass you, it's much quieter, which is normal. It's basically the opposite of everything else you've ever heard, which is super cool because it changes frequency as it moves. So frequency increases as it moves towards the object, and it decreases as it moves further away. Which, sounds like everything would do that. And things kind of do, but when it's coming towards the back of you, you can hear it. And then as it moves further away from you, the sound gets louder. So the source of the waves must be moving in respect to the observer. So if you are standing right beside the ambulance, you're not going to experience the Doppler effect. The Doppler effect has to be moving towards you and then past you. Now, astronomers also use this for stars, which is very neat. So now, the most often, though, is when we experience them with sound waves, but the Doppler effect can also be used for light waves. All right, so keep on going. So we have, as fire trucks move towards the kids, we have shorter wavelengths, which means higher frequency and much higher pitch. As it moves away from the kids, it's a lower wavelength with lower frequency and a lower pitch. So it sounds like it is getting quieter as it goes away, and it's getting louder as it comes towards you from behind. So it's very, very neat. All right, so make sure that you have filled in everything on your foldable.